All right, let's get started. Welcome to class. This is week 4. We have some interesting stuff to do today. We're going to talk a little bit more about the birthday problem that we left off with last time. I just want to make sure you guys understand how the counting methods are come into play with that, and how you can calculate probabilities based on those sorts of things. We'll also talk about a little bit about Bayes' theorem, because I know there's a homework question that you probably are going to ask about that one. So we'll do homework questions from the homework that's due this week, and then we'll talk a little bit about some of the Chapter 6 stuff that has to do with discrete random variables. So that's what we're going to do. I will also remind you that 2 weeks from today is the midterm exam, and I will talk more next week about the location and kind of the format, and help you get ready for that. So look for that next week. So when you guys learned about how to count when you were little kids, you said, okay, here's the number 1, and then 2, and then 3, and so forth. And eventually you got to this major milestone in your life where you could count up to 98, 99, and then 100. Right? You guys remember that? It was fun. It was exciting for your parents. And well, counting is something that I think I mentioned last time can be a little bit more involved than just doing this. And we talked about the multiplication rule. If we have a process that has sub-processes and we want to know the number of ways we can perform the process, just multiply the number of ways we can perform each of the sub-processes. And so one of the things that tends to show up quite often is not just counting, but adding up these numbers. And it turns out there are kind of slick ways to think about this that use the notion of counting that we've talked about already. So if you had to sit down and write the sum from 1 up to 100, how long do you think that would take you to do? Like 15 seconds?
A day.
A day? I think you could do it quicker than a day. If you had a computer to do it for you, you could do it really quickly. Well, there was a guy named, what was his first name? Carl? Carl, yeah. And he was smart, one of these prodigy kids that could do lots of things. And so when he was in school, he wasn't really challenged. And so he got to be a little bit rambunctious, and today he probably would have been put on ADD medication. But one day he got in trouble. This was back in the 1800s. And his teacher said, "Carl, you're a bad kid. You're not going outside for recess with everybody else until you pay the penalty for what you did. And the penalty is, the price you have to pay is you have to add up the numbers from 1 to 100. And the teacher thought, oh, this is going to be great. It's going to take him like a week's worth of recesses. And actually, I think the story was maybe 1 to 1,000, but some crazy number. And so Carl said, well, okay, I guess I'll do that. And this was back before the days of paper and pencil. They had slates and chalk that they would use. And so all of his friends went out to recess, and he sat down at his table or his desk and started writing. And about 15 seconds later, he stood up, walked over to the teacher, threw the slate on the desk, and said, "I'll see you later." And the answer to the question was 5,050. So how did he do it so quickly, do you think?
Well, I did it 50 times 101.
50 times 101. Okay, so you would have gotten out early. Good. Congratulations. The rest of us would have said, I don't know. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, and so forth. And what Gauss did is he said, if I take the first and the last numbers and add those together, I get 101. And if I take the second number and the second to last number and I add those together, what do I get? 101. And I keep doing that. How many 101s do I have? And it turns out to be there's 50. And so the answer to this sum can be written as 100, that's the number that we're adding up to, times 101 divided by 2. And it turns out this is always true, even, you might look at this and say, well, 100's even, and so if we multiply by an even number, but even if we're adding up to an odd number, it still works, because the next number after that is even, so we're always going to be able to divide by 2. So this is an interesting number, and it turns out that we talked really briefly last time about combinations. Turns out the combinations is very closely related to this. Remember we said with combinations we're going to choose from n objects, we're going to choose R from n objects. And we said the way that we're going to do that is we're going to say there's n factorial ways that we can write down or put all of the objects in order, I should say. And then I don't really care about the order of the n minus r objects that I'm not selecting, so I'll divide that by n minus r factorial. But I also don't care about the order of the r that I am selecting. I'm going to divide that by r factorial. Well, if n is this is going to be, I shouldn't do this. Let's say r is equal to 2, then what do we get? And this is called, we write this as n choose r. N choose 2 is going to be n factorial divided by 2 factorial divided by n minus 2 factorial. So that's going to be n times n minus 1 divided by 2, which is similar to what Gauss said. Remember, this was n times n plus 1 divided by 2. So how is this different? Combinations are just saying I'm adding up the numbers from 1 to n minus 1, right? So if I have n minus 1, that's n minus 1 times n divided by 2. So what does it mean to have a combination? If I have n objects and I want to choose 2 of them, what does that mean? Okay, if I've got 40 students in the classroom and I want to choose 2 of you guys to say how many pairs or how many ways can I do that, that's just going to be 40 choose 2, right? So imagine you go into a classroom or a party or whatever, and you shake everybody's hand. You meet everybody at the party. How many handshakes did you have? Well, you can't shake hands with yourself, but there's 39 other people in the room, so you shake hands with 39 people. Okay? the next guy, we've already counted the handshake that you had with the next guy, so how many handshakes does he have that already haven't been counted? Well, now there's 38. And then the next guy, 37, 36, and so forth, all the way down to the last person who, the last two people who shake hands with each other. If you were to take a matrix and say, here's 1, 2, 3, 5, 6. Let's just say 6, and then there's 1, 2, 3, 4, 5, 6. If you guys know about symmetry, symmetric matrices, I should just shut up, right, and just drop this and move on. Okay, never mind. We'll just get rid of this. Forget I said that. There is a really cool application of what I was just talking about with symmetric matrices, which anyway are used for correlations. So if you have the correlation between two variables, then you've got a number between -1 and 1. If you have 3 variables, then you have how many correlations? Well, it's 3 choose 2, which is 6 correlations. No, 3 correlations. You have 4 variables, and you're going to say how many correlations are there. It's the same thing as saying how many pairs are there. Anyway, okay. So let's continue with this then. If I wanted to say what's the probability that at least 2 of us have the same birthday, what does that mean? It means we have at least 1 pair of students in the class that have the same birthday. But it's possible we have 2 pairs. It's possible we have 3 pairs, or 4 pairs, or 5 pairs. It's possible we have up to how many pairs? If there's 40 people, we could have 20 pairs. Right? But we could also have 10 pairs and then the other 20 people without the same birthday. Or we could have 3 people with the same birthday. That would be at least 2 people with the same birthday. And we could have 3 people with the same birthday, and we could have pairs of people with the same birthday. Or we'd have 3 people with the same birthday and 3 separate people with the same birthday. So there's lots of ways that this probability can take place. And just to show you how fast these things grow, let's call this combination. And let's call this, let's call this n equals 40. So here's R, and then we've got combinations when n equals 40. Okay, so the number of combinations that we have is going to be equal to, there's a function built into Excel. You should probably learn how to use this if you have your HP48GX calculator or your TI-83 calculator. There are functions built into that as well for doing this, but I think it's good to learn how to do it in Excel. The function is called combine, or combinations, combin, and we're going to put 40 comma B2, and I haven't populated B2 yet, so I'm going to say put in a 2 right here. So if I have 40 people and I want to select 2 of them, that's the same thing as saying how many pairs of people do I have out of 40. Well, it turns out there's a lot, 780 pairs. And we probably have close to 40 in the class today. So you can imagine I'm going to pair off everybody, right? How many ways can that be done? 780. That's a lot. Do I want to do that? No, it takes too long. I have a computer do it for me quickly. But what if I have, how does this relate to the birthday problem? If I have 2 people and I say, what's the probability 2 people have the same birthday? What would you say? Same day of the year. Say, well, it doesn't matter what day the first person's born on. Whatever that is, just fix it. And then the second person can be born on 365 days of the year, but only one of those matches the first person. So the chances of having two people with the same birthday is 100, or 1 divided by 365. You could ask the same question about days of the week. In fact, my brother interviewed at, he works at Deutsche Bank now, but when he was just finishing his master's degree, he went around and interviewed all these places, and banks in New York and whatever, and they said, you see those two people sitting over there at the desk? And he's like, yeah. What's the probability they're born on the same day of the week? And they wanted to see how he thought about things and probability and his understanding that, and he said, well, he went through the same argument, and chances are 1 in 7 that they were born on the same day of the week, given certain assumptions. And then they said, okay, so if it's 1 in 7, how much will you bet that that they're not born on the same day of the week, or that they are born on the same day of the week? You take your pick how you want to bet. And of course they wanted to know what he was thinking about the assumptions that are being made. And the right answer to that question is, well, if those two people are randomly selected and birthdays are uniformly distributed, then it's 1/7. And if I'm picking the people, then I would say the probability is 1/7. If you're asking me for two people that you've already picked out, then the probability is not 1/7. You probably rigged it, and they do that sorts of thing on Wall Street all the time. So 1 in 365 is the probability two people have the same birthday. We've got 780 different pairs of people. So that's going to have a big effect on the probability that at least two people have the same birthday. Now, I said a minute ago, what if we had 3 people with the same birthday? Oops. Well, how many ways can I choose 3 out of 40 people? Turns out there's almost 10,000 ways that I could do that. So if I had to just randomly pick 3 of you guys, order doesn't matter. If I had to randomly pick 3 of you, there's almost 10,000 ways I could do that. Is that not crazy? That is crazy. What happens if I'm choosing 4? Well, I'm just going to populate this all the way down here. And I'm going to keep going, actually. Okay, what happens is I get, where's this going to max out? It's going to max out at 20. 1.37 times 10 to the 11, isn't that 13? That 100, how many billion is that? 10 to the 9 is billion. So that's 137 billion. Am I right about that? It's either that or 13 billion. That's just, you got 40 people sitting in this room. How many ways can I randomly, or not randomly, systematically pick 20 of you guys? Split the class in half. Right, so that's not a trivial task, is it? I'm going to split the class in half. How many ways can I do it? A lot, like billions, tens of billions. What's the easiest way to do it? Alphabetically, probably. I don't know. You can only do it if it's even, of course, but to split exactly in half. So all of these numbers, all these big numbers, and even more, right? If we were to go all the way up to 40, what do we see? 40 choose 1. There's only one way that can happen. But in the context of the birthday problem, what does that mean? It means everybody's born on the same day. Is it possible? Sure. Why would it be impossible? I can guarantee you there's 40 people in this city that all have the same birthday. Right? I mean, there's millions of people. Who's to say I didn't randomly select them? It's very unlikely, extremely unlikely, but it could happen. But all of these scenarios and more need to be taken into account. Notice, however, when we get down to here to 38, look at that. 780, does that look familiar? 37, 988, 0, that looks familiar. Why? Because this is a symmetric function. But I really need to take all that into account if I'm going to calculate this probability. Or I don't have to take any of it into account if I do it in the right way. In other words, what I just described is way too complicated. But it's complicated enough that I can make things very simple by taking what's called the complement. And I say, if at least 2 people have the same birthday, that's the complement of everybody having a unique birthday. So what's the probability that no one has the same birthday? We'll say no shared birthdays. And I just subtract that from 1. Okay, so that's something I can deal with. The other stuff I can't deal with. Because, I've got 780 different ways for me to pick one pair. And then if I've got one pair, is it possible somebody else has the same birthday as them? Is it possible other people have shared birthdays? It's just too crazy. But this I can write as 1 minus, let's write this, let's just kind of draw this out. How many days can the first person be born on such that everybody has their own birthday? 365, right? There's no restrictions for the birthday of the first person. Whoever that first person is, doesn't matter who it is. How many ways can I pick, or how many days can the second person be born on? 364. How many days can the third person be born on? 363, 362, and so forth, down to 365 minus 40 plus 1. Okay, so this is not a probability. This is just a big number. How do I turn it into a probability? I divide by something. What do I divide by? The number of days that the first person can be born on without restriction, which is 365. The second person, if there's no restriction, can be born on 365 days. 365, 365, 365. So this turns out to be 1 minus 365 factorial divided by 365 minus 40 factorial, all raised to the 365 to the 40th power. Okay, so if you think about it in the simplest way possible, this actually isn't that hard of a problem, is it? No, we're just saying what's the probability no one has the same birthday? Well, I can write that down fairly easily. Turns out that I think we mentioned permutations last time. This is 1 minus permutation of 365 objects taken 40 at a time divided by 365 raised to the 40th. Okay, so what's a permutation? Permutation in R, sometimes it's written like that, sometimes it's written like this, sometimes it's written as your calculator, your Texas Instruments probably writes it like this. This is going to be n factorial divided by n minus r factorial. So it's actually n factorial divided by n minus r factorial, also divided by r factorial times r factorial, and this is just r factorial times and choose r. Okay, so that's bigger than combinations. If R is, R can be large, permutations is going to be much bigger than combinations. So we can plug this in. In fact, let's come over here. This is combinations. I'm going to insert, put permutations. So n is still 40. In Excel, the function is permute 40 comma C2. And so if I'm taking if I'm selecting 2 of you guys, so 2 out of 40, but I care about the order. In other words, if I pick Jeff first and then Samantha, that's different than picking Samantha first and then Jeff. Right? Permutations, order matters. Combinations, order doesn't matter. So if I'm selecting 2 of you guys and order matters, it turns out there's 1,560 different ways in which I can do that. Okay, so that's quite a bit bigger. And you see that permutations just keep going and going and going. All right, so there's no symmetry here. If I have 40 40 objects and I want to take permutations of size 40, what's that really saying? It's saying what's 40 factorial? So 40 times 39 times 38 and so forth. And you see that's very, very large. Okay, so to get this birthday problem, what am I going to do? This is going to be equal to 1 minus the number of permutations divided by 365 raised to hold on, raised to this power right here, but let me insert. So I actually need to copy this stuff and paste it in here again and change this from permutations when n is equal to 40 to 365. And so this needs to change to 40, 365. And I actually don't want this anymore. So. Alright, so this birthday probability is going to be 1 minus change that to E2. Alright, so that number divided by 365 raised to that number. So if I have 2 people in the same room, or only 2 people, the probability is really low. If I have 3 people, you can see it go up. Where does it hit 50%? It hits 50% when I have between 22 and 23 people. So if there's 23 people in the room, probability is 51% almost that at least 2 of them have the same birthday. Now the question that I asked you guys, when I asked you guys on Friday or last week about this, we said there's 40 people. Probability is about 89%, about close to 90%, which is pretty high. Okay, so but look what's happened to the permutations. We're already look at this. We're already at 3 times 10 to the 101. Anybody know what that number is bigger than? It's got a special name. You have guaranteed heard the name thousands of times. Google, yes. Except for you spell it Googel. And the guys who invented Google.com, smart as they are, didn't know how to spell Google, so they spelled it Google. But it's the, yeah, that's a big number. We can keep this going. And you can see what the probability ends up being. Oops. Okay, I don't know what happened there. Let's just get rid of that. But the probability keeps going up and up and up. But look what happens to this permutation number. Do we have the right permutation here? Yeah. It gets so big. We're at 6.5 times 10 to the 173. That's incredibly large. But what are we dividing by? We're dividing by 365 raised to that power, which is bigger. It's always going to be bigger. It gets to be much, much bigger. And at this point, this probability is, I don't know why this didn't work. Why didn't this work? Why is it giving me negative values? Anyway, I'll have to troubleshoot that later. But the probability keeps going up and up and up, which is very interesting. And so we've got combinations. And we've got permutations. And these are the basis for what's called the hypergeometric distribution, or at least combinations are. They're also used, combinations are in something called the binomial random variable. We'll talk about that. But before we do, I just want to do one more example of where combinations come into play. And that is in one of my favorite games of all time called Guess the Secret Serial Number. Has anybody ever played this game before that you know of? Well, it's pretty simple. Here's how it works. I'm thinking of a 6-digit serial number, and you guys try and guess. Now, you might be wondering, is this really a game I play? And the answer is yes. I grew up in the West. My wife grew up in the West, and still have family out there. So with 4 kids, to fly out to the West every summer is challenging financially. So instead of flying, we just drive. And it's 3 days in the car, and the kids are bored out of their minds. So we say, okay, well, let's play a game. I'm thinking of a 6-digit number. And you can't imagine how exciting it is when somebody finally gets the 6-digit number. So let's just try it. A couple rounds. Yeah, you. 6 digits. Yeah.
6, 5, 9.
Nope, that's not it. Sorry. Who else wants to play? This is really fun. In the back. Yeah, you moved. You blinked. Yeah, go ahead. 2, 3. No, that's not it. You clicked your pen back there. Come on, give me a 6-digit number.
1, 2, 3, 4, 5, 6.
No, that's kind of obvious guess, but yeah, you scratched your. Yeah, your turn. What? Yeah, you, and then you. Yeah, you talked. So you. Yeah, go ahead. No, that's not. No. Go ahead.
4, 4, 4, 4.
No. Well, you said 7 numbers there.
No,
Because you almost had it right, but no.
I said 6.
Oh, you said 7. Okay, never mind. I thought I heard 7. Okay, so this is a really fun game. You guys are all having fun, right? We could spend the rest of the class playing this, couldn't we? Yeah, how many guesses would it take on average till we win? A lot. It turns out blockchain, you guys know about blockchains? Blockchains are basically computers just doing that over and over and over again. All they're doing is guessing randomly at a number, and if they get the number right, then the blockchain gets verified and it gets pushed out to the public, and everybody else says, okay, let's build on that one now. But that's basically what's going on with blockchain. I mean, seriously, that's exactly what's going on, except for they have like 34-digit. Hey Siri.
I found.
Yeah, be quiet. I don't know what. Did I say anything?
You said seriously?
Oh, serious. Oh, I hate that. Good. I'm never gonna say that word again. Okay, so what could I do to make this popular besides give you a big reward for guessing? Nothing. I can't do anything to make it popular without giving you a reward. Who in their right mind would want to play this game at all if there was not some promise of a big reward? Anybody? Anybody want to play it? No? Okay, what kind of reward is it going to take? What about 12.5 bitcoins?
Yes.
Okay, so every 10 minutes, 12.5 bitcoins are given away to the lucky computer that does this. For I think they're on 34-digit binary, so 2 to the 34 is the number of possible guesses. So it's much bigger than 6 digits. Okay, so other than that situation, how else could I do this? I mean, 12.5 bitcoins, that's only like $100,000, right? 120? 120, so it's, okay, so it's still above the 10,000. But that's not that much money, is it? I mean, a month ago it was twice that. What about like $1 billion? Think anyone would play this game for $1 billion? Like, how much would you pay per guess to play this game? $2, right? Oh, is this just the lottery? This is just the lottery in disguise, isn't it? So you guess numbers, and I tell you if you're right or not. And if you're right, I'm going to give you a lot of money. And if you're wrong, then you're going to give me a little bit of money. And we're going to just rig the system. In other words, we're going to say this last number is anything between 1 and 39. So it's more than a 6, could be more than 6 digits, right? So you pick, that's called the Powerball. That's the red one. And then we have 5 white ones that are between 1 and 59. See, it's just, I mean, that's all it is. You just guess numbers, and if you get them right, you earn money. I mean, pretty cool, huh? How many ways can you choose 5 of those white numbers? Well, how many choices do I have for the first one? 59. And then how many? 58. 57, 56, 55. How many do I have for the Powerball? How many choices are there? 39, right? Powerball can repeat. It's like its whole different bin, whole different set of ping pong balls. So is that it then? Do I just multiply all those numbers together to find out how many possible lottery tickets there are? No, because I don't have to get the first 5 in order. Do I? No, I don't. In fact, when they release them, they put them in order for me. I don't have to worry about that. So that means that we're dealing not with permutations, but with combinations. And we say, how many ways can we rearrange those 5 numbers? And that's the total number of ways that I can get all these numbers. So what is this? This is 59, choose 5, times 39, choose 1. And that turns out to be a big number. Now they manipulate this number and this number every so often. They change those things when they want the number of tickets that can be sold to change. And the reason they do that is because sometimes, well, so when I first moved to Philadelphia 15 years ago or so, the biggest the jackpot ever got to be was like $350 million. And when it would get that high, back in those days, it was only $1 to play, $1 per guess. Everyone would get all excited, and people that lived in states. I lived in North Carolina before here. There was no lottery at the time, and so when the Powerball got bigger than this number, or sorry, when the payout got bigger than that number, people from North Carolina would drive to Virginia to buy tickets because you couldn't buy them in North Carolina, and especially the math people that said, oh hey, if the payout is bigger than the number of tickets, then there's actually a positive expected value, and so they would go and do this. But it got to be really hyped up. The news people, local news channels would interview, like I remember they interviewed one of the Philadelphia Eagles, and he said, yeah, that's a lot of money, $350 million, wow. And they interviewed me, and they said, what's the probability of winning now? And I said, well, it's the same as it was before, and it says it right here on the ticket. Just read it right off the ticket or go to their website. It says 1 in 195 million. That's what this number is. So we go over to Excel and we can calculate this. So here we have combine 59,5 times 39. 39, choose one, is just 39. So we'll leave that there. And we see that we have 195,249,054 different possible winning or possible tickets, only one of which wins. So the probability you're going to win is 1 divided by that number. And so probability of winning is just going to be equal to 1 divided by that, which is a very small number, 5 times 10 to the minus 19. Well, what if your investment what if you decided to treat this like an investment strategy? I'm going to buy tickets every week, and it's actually kind of sad because now they let the jackpot go up as high as it can go. So I think it was $1.4 billion a year ago or something like that, and I think 3 people won it, or anyway. But they go around and they interview all these people that are standing in line waiting to buy lottery tickets. And what do they say inevitably? It's my turn. I've been doing this for a long time, and it's my turn. Someone's got to win, and it's my turn. I deserve it. Just look. Here's a list of all the good things I would do with the money. I would help people. I would, all these things. You guys know what Riverdance is? You guys know Riverdance? The Celtic dance show. It's kind of like a Broadway thing. The Riverdance cast one time was an interesting radio program on NPR that they interviewed these people. They said, look, we're going to win the lottery, and we're going to dedicate our performance to this lottery, and it's going to bring so much positive energy that our pool of lottery tickets, and they had everybody in the cast was like just buying lottery tickets, it's going to make us win, and we're going to split it up, and they believed it, and the performances apparently were just out of this world, and it was their turn. They put so much effort and energy into it. Did they win? No, they didn't win. Who won? I don't know. Somebody did, I guess. But the lottery doesn't care about you. It doesn't care about me. It's not your turn. It's never going to be your turn in that sense. In fact, if you played $20 a week, which is 10 tickets a week, you could say, what's the chance that you're going to win? Well, it would roughly be 10 times this number right here. And so you could say how many weeks should I expect to wait until I win the lottery at $20 a week? And that's assuming that the price of tickets don't change. Well, it turns out that you should expect to wait in weeks that number 195 million divided by 10. So 190, so whatever it is, 19.5 million weeks is how long you should expect to wait. And just to help you put that in perspective, what's that in years? That number divided by 52, it's about 375,000 years. So if you're going to do the lottery, please do. I mean, if it's something that you're interested in, you think it would be fun to buy lottery tickets to give to somebody for their birthday or Christmas presents or whatever. But just know that it's a losing proposition. I mean, the expected value is negative, expected winning is negative, and but I'm fully supportive of you doing it, because then I don't have to pay as much in taxes. So the lottery is really just a tax against people that don't understand math, and or they don't care about that and they just want to go out and have a fun time, and there's some entertainment value in it. I will admit that. So so yeah, lotteries are interesting things. So questions on the homework. Let's look at questions on the homework. So we have homework number 3. Number 6. That's it. Number
12 and number 18, please.
12 and 18. Okay, any others? Well, you can think about it, and we'll do these and then see where we're at. If you have more questions you want to ask, certainly can. Okay, a web server hosting company advertises 99.999% guaranteed network uptime. How many independent network servers would be needed if each has a 95% reliability? All right, so number 6, we have the probability that the network is running is 0.99999. I get that right? So 5 nines, right? So what does this mean? How does this work? We have individual servers that have probability a server is working is 95%. So they've got a bunch of different computers that are doing exactly the same thing. They're all accessing a hard drive system that is, some big RAID hard drives, a bunch of hard drives that can be accessed from any of the servers. And so basically what they're saying is what? How many of the servers are up at any given time? Well, they're saying there's a 99.9999% chance that at least one server is running, right? Okay, so this here is the probability that at least one is running. Okay, so if at least one is running, how do we find the probability that the system is not working? In other words, what's probability the network is not up? One minus what? Okay, so it's 1 minus the probability that it's up, which is 0.99999. How many nines that is. Okay, does that help us? It's true what we wrote down, but what does it mean for the system to not be running? All of the servers are down. Okay, so what's the probability that all of the servers are down? Well, I don't know how many servers we have, but so what's the probability any particular server is down? So the I just says, in general, one of the servers. So there's a 5% chance any of the servers are down. And so the probability, if these things are independent of each other, which typically they are, it's not always the case. If the building they're in loses power, then if all the servers are in one location, then they're all going to go down. So that's not independent, but these big companies, Amazon and Microsoft and Apple, they've got servers all over the place. So if the power goes out to the Northeast, New York, Philadelphia, their company's not going to be affected by that because they've got stuff in Los Angeles and Chicago and wherever else they're storing this stuff. China, Japan, all those places, Russia. Okay, so this is going to be probability that all of the servers are down, which is going to be 0.05 raised to the nth power. And we don't know what n is, but that's what we're trying to find, is we're trying to find n. So this makes sense. If all of the servers are down, that happens with probability 0.05 raised to the number of server power, the number of servers that we have. Power, so 0.05 times 0.05 times 0.05 if you have 3 servers. So the only thing I don't know here is n. So 1 minus 0.99999 is equal to 1 minus 0.05 raised to the nth power. And so what does that mean? 0.05 raised to the nth power is equal to 0.99999. Is that right? That can't be right because it doesn't work. Let's see. So we want to, let's see, we got 1 probability the network is down. That should not have a 1 minus, it should. Yeah, there we go. That works. Yeah. Okay, so you see what I did here? I said this is probability the network is down, and the probability that the network is down is the same as the probability that all of the servers are down. So this is 1 minus 0.05 raised to the nth power. So make sure you get your parentheses in the right place. And so now we can solve this thing for n. How do we solve this for n? We're going to use logarithms, right? So logarithms just say, if I take 0.05 and raise it to the nth power, what value of n gives me 1 minus 0.99999. And so I can do this log base 0.5 of 1 minus 0.99999. That's n. Or I could take the natural log of both sides, so natural log of 1 minus 0.99999 is equal to n times the natural log of 0.05, and so n is equal to the natural log of 0.05, the natural log of 1 minus 0.99999 divided by the natural log of 0.05, and those things should be equivalent to each other. So let's come over here to Excel. So this is homework 3.6, and we have probability of the network, and we have probability of the server. So this is 0.99999. This is 0.95. So n is going to be equal to the log of 1 minus that thing, comma, the base, which is 1 minus that, which means I wrote this down wrong. Oh no, I didn't. Yeah, log of, here I put it wrong. Log of base 0.05. If I want to do it the other way, this is going to be the natural log of 1 minus that thing divided by natural log of 1 minus that. And those are the same. So how many servers do I need? I need 4. Why do I need 4? Because the answer was 3.84. I can't have 0.84 of a server, so I'm always got to round up on that. If I round down, then my reliability is not going to be that high. So I always have to round up, and it says minimum 0.99999. What would happen if I used 4 or 3 instead of 4? What would that do to my reliability? So this is we take 0.99, so 1 minus raised to the 3rd power I need a 1 minus that too. Okay, so if I've got 4 servers, then I get 0.99999, and then I actually get a little bit extra. If I had 3 servers, I would have 0.999875, so I wouldn't have the same reliability that I promised. Okay, so that's 4. How many independent network servers would be needed if each has 86% reliability, which is probably more accurate? I'm just going to copy this, paste it in. All I have to do here is change this from 95 to 86%, and we get 6. So make sure you round. If you don't round these things, you're going to get them wrong. Okay, so that's number 6. Questions on that before we move on? Did you see how it was kind of similar in some regards to the birthday problem? You didn't? So the birthday problem, we said, what's the probability at least 2 people have the same birthday? We said, well, that's kind of complicated because we could have pairs and so on and so forth. So we said, let's just take 1 minus probability that no one has the same birthday. So with the server reliability, we said, or for the network, we said, what's the probability that the network is up? Well, that's just 1 minus probability that it's down, and it's down when all of the servers are out. So instead of having to say, let's just say I had 3 servers, then the network's going to be up if all 3 are running, or if 2 are running, or if 1 is running. There's 3 ways I can have 1 running. There's 3 ways I can have 2 running. There's 1 way I can have 3 running, but there's only 1 way that I can have none of them running. So that's very similar. Okay. Problem number 12 says a biometric security device using fingerprints erroneously refuses to admit 3 in 1,200 authorized persons from a facility containing classified information. The device will erroneously admit 3 in 1,002,000 unauthorized persons. Assume that 98% of those who seek access are authorized. So this is, first of all, we're told that, what are we told? Erroneously refuses to admit. Okay, so somebody is not admitted given that they're authorized, and the probability of that happening is 3 divided by 1,200. I got that number right? Yeah, 3 over 1,200. Okay, what else we need? The device will erroneously admit 3 out of a bunch of unauthorized persons. So given that somebody's not authorized, the probability that they will be admitted is 3 divided by 1,002,000. Okay, so what else are we told? We're told that the prior probability that somebody is authorized is going to be 98%. So what do you see here? 3 out of 1,200, that's 1 out of 400 people that are authorized will not be admitted to the facility. So you guys have all seen the movie Incredibles, like Edna Mote and Elastigirl. They show up, and what happens? They're not admitted. Big machine guns come out, and they're like, "You're dead now." Well, I guess that doesn't happen because 1 in 400. If this is a big facility that has, say, 1,000 people, every day you're going to have at least a couple, on average, that are not admitted that work there. Okay, so that's kind of set low, or sorry, that's set a little bit high. The other case is a little bit more troublesome. If somebody's not authorized and they're admitted, that happens 3 out of 1,000,000 times. So that's quite a bit less. They're much more strict about, or the system's much better at keeping unauthorized people from getting in than it is from keeping out authorized people. Okay, so what's going to happen then? Somebody is going to be refused admittance. So somebody doesn't get in. What's the probability that they are, I think they want to know authorized. Probability they are authorized. Yeah. So somebody doesn't get in. What's the probability they're authorized? In other words, they go, they swipe their badge, they do their fingerprint scan or whatever, and it says, sorry, you can't get in. Does this have practical applications for you guys? Yeah, because you guys have phones that like read your fingerprints, right? If somebody steals your phone, what's the chance they're going to be able to get in? Well, the system's not perfect. So what's the probability that if they're not admitted, that they were actually authorized? In which case, everything's going to be okay for them because the machine guns are going to get turned off. So how do we answer that? We're going to use Bayes' theorem, which says this is the probability of not being admitted given that you're authorized. I should maybe write up here, AD means you're admitted, and AU means that you are authorized. Okay, so Bayes' theorem says probability you're not admitted given that you're authorized times the prior probability that you're authorized divided by the probability that you're not admitted. Okay, so in other words, we've said we know that something has happened. Somebody's not admitted. So there's like, some events taking place. Given that event, that changes the space of the universe. That changes the universe. If we don't have that information, we know the prior probability or the probability of authorization is 98%. But now they've been denied. How does that 98% change? That's what we're asking here. Okay, and that's going to be based on these things. How accurate is the scanner? So the first thing we need is the probability of not being admitted. And that can be written as the probability of not being admitted given that you're authorized times the probability of being authorized. That's one way that you can be not admitted. What's the other way? If you are not authorized times the prior probability of being not authorized. Do we know the probability of being not authorized? The unconditional probability? Sure. How do we know that? Law of complements. That seems to be a recurring theme today. So 1 minus 0.98 is 0.02. There's a 2% chance somebody is not authorized. Without having any information, everybody walks up to the door, we'd say there's a 2% chance you're not authorized. And so this screening process is really just saying we want to change that probability. We want to improve from there being a 98% chance that you're authorized. We want to improve that so that it's higher. And this is how it does it. Okay, so I know this part here, and I know that part, and I know that part. So I can write this down. The first one is 3 out of 1200 times 0.98. Over here we have times 0.02. But what are we multiplying by? Do we know that thing? No, we don't know it. We haven't written it down yet, but we can write it down. It's the probability of not being admitted given that you're not authorized. And all of the laws of probability that we learned so far are true for unconditional probability, but they're also true for conditional probability if we condition on the same thing. So in other words, we're saying let's condition on this not being authorized. So this is just going to be 1 minus 3 divided by 1,000,000 2,000. So I can plug that in here. 1 minus 3 divided by 1,000,000 2,000. And what do I get for this probability? Let's come over here. Homework 3.12. We've got probability of not being admitted given that you're authorized. We've got the probability of being authorized. Wait. Probability of being admitted given that you're not authorized. And this one is 3 divided by 1200. And this one is 3 divided by 1002,000. And so we want the probability of being not admitted given that you're not authorized. And I just said that's going to be 1 minus that thing. So it's extremely accurate. And then what else do we have? Probability of being authorized is 0.98. And the probability of being not authorized is just equal to 1 minus that. And so finally we need to find the probability of not being admitted. And I'll do it right here. Probability of not being admitted. And I just said that's going to be equal to this number, 3 divided by 1200, times the probability of being admitted, or being authorized, plus probability of not being admitted given you're not authorized times the probability of not being authorized. So there's a 2% chance that someone's not going to be authorized. Sorry, not going to be admitted. Every single person who walks up, there's a 2% chance. Okay, so what do we want now? We want probability of being authorized given that you're not admitted. And this is just going to be equal to probability of not being admitted given that you're authorized times the prior probability of being authorized. This is 0.98. And all of that's going to be divided by that 2%. What's that? Is it? 10%. Given that you're not admitted. So if that is unusually high, that means that maybe I'm going to check my math here. So I have that number. Yeah, that's right. Okay, so is this right? I think this is high, isn't it? So that number times 98% plus that number is 2%. Okay, so how could we think about this? Okay, so if we had 1 million people show up, of those 1 million people, how many are authorized? 98%, right? So we have 1 million times 0.98. That's 980,000 people that are authorized. Of those 980,000 people, how many are going to be not admitted? So 980,000. What's the admittance rate for those people? So if you're authorized, you get in almost all the time, right? So we're going to say what proportion are not admitted, because that's what we're really interested in. So it's 3 divided by 1,200, or 1 in 400. So I'm going to multiply that by 3 over 1,200. And of the 98,000 people that are authorized that show up, I have 2,450 that are not admitted. Right? That's 980,000 authorized people show up, they're not admitted. Okay, of that same 1 million people, how many are not authorized? 20,000. Right? So we have 20,000 that are not authorized. They show up. How many of those are not admitted? Well, it's 20,000 times this number here, which is basically 20,000. So if I take 2,400 and I divide 2,400 by 2,400 plus basically 20,000, what do you think I'm going to get? It's about 10%. Wait a second. That's the same number that we just calculated over here. So what's going on with Bayes' theorem? And you can think about this in terms of a disease, a medical, a disease. You go into your doctor and they say, well, the prevalence is 1 in a million, and the test is really accurate. It's 99% accurate if you have the disease, and it's 99% accurate if you don't have the disease. So 1 million people come in. How many positive test results are you expecting? Well, of those that don't have the disease, given you don't have the disease, what's the probability of a positive test result? It's 0.01. So 0.01 of a million is still pretty big, isn't it? 1% of a million? It's 10, what is that, 10,000? If you do have the disease, then the probability you're gonna come back with a positive test result is 99%. Well, how many people have the disease? Just 1 in a million. So you have 10,000 people with a positive test result that don't have the disease. That's because the test makes a mistake. Then you have 1 person that does have the disease, and they get a positive test result. So 1 divided by 10,000, that's the probability that you actually have the disease given a positive test result, which is pretty small. But that's not why you go to the doctor, because the doctor says, well, if you were to walk in off the street, we'd say the prevalence is 1 in a million. But given the symptoms that you've got and the, my expertise as a doctor, I think the probability is higher than 1 in a million. Maybe it's 1 in 2. If that's the case, then that changes things. But that's the idea going on behind this. And if we come over here, we can copy and paste our value in, and we see that it is in fact about 11%. Right. I think this actually does make sense, doesn't it? If you have a bunch of people showing up that are authorized, most people that show up are authorized. There should be a high probability that if they're not admitted, they're still going to be authorized. And so this is saying the person is not admitted. What's the probability that we have to then prosecute them or get somebody to go after Tom Cruise when he runs off with the whatever it is he was trying to steal from the place? All right, so number 16. All right, we're just going to push through, and then we'll stop at least 10 minutes before we normally would.
When you do some more calculations, can you do more of them like on the board rather than Excel? You do have to follow Excel.
Oh yeah, so you want me to fill this in so you can see where the numbers, yeah, that's a good idea. So I don't know what that is. I'm going to go back to Excel because that's how I calculated it, but it's so 0.0202244. So when I come up here, I get 0.0224499. That's the denominator, and the numerator I have 3 over 1200 times 0.98, and that turns out to be 0.10913. Is that what you're hoping for? Okay. Yeah, good point. Come back and yeah. All right, so it's number 16. Is this the other one, or was it 18? 16, 18. Sorry, I don't want to be solving problems you guys don't have. They're not problems. At Oxnard University, a student ID consists of 2 letters followed by 5 digits. How many unique student IDs can be created? At this point, this is the point where I like to say, instead of figuring out that problem, why don't we just play a nice round of guess the unique student ID? What do you guys think? You want to play that? No? Oh, come on, you shook your head. Just go ahead and guess. You got 2. If you get it right, you get a Bitcoin. I don't know where you're going to get one of those, but homework 318. All right, so we have 2 letters followed by how many numbers? 5. 1, 2, 3, 4, 5. All right. Any other information we need to know here? Yeah, so it doesn't say anything about like the digits not being able to repeat, or you can't have 0 0 0 0 0 or anything like that. So how many choices do we have for the first one? 26, right? 26 letters in the alphabet, 26 letters in the alphabet. And then now we're to the numbers. There are 10 digits, 10 digits, 10 digits, 10 digits, and 10 digits. So this is 26 squared times 10 to the 5. Whatever that turns out to be. Come over here. So what is that? 67 million. Would 2 letters followed by 3 digits suffice for a university with 49,500 students? So if there are only 3 numbers following, is that going to be enough? So 26 squared times 10 to the third. So all we have to do is divide that by 100. Let's just copy and paste that to a 5, to a 3. So we have 67,000, or sorry, 676,000. So yeah, that should be enough, shouldn't it? I'm going to say yes. Check our work. And looks like we got it right. Okay. So other questions from homework? Which one? Yeah, so we have two letters followed by 5 digits. So it's kind of like Drexel ABC 1 2 3, but instead of it being assigned to your initials, it's actually just randomly generated. So letter, number, and number. Okay, so what was that? 6, 7, 6, 1, 2, 3, 4, 5. I don't know, whatever, however many numbers that is. That's what we get. Okay, so other questions on the homework? Number 9. Okay, levels of cockpit noise in an aircraft can damage the hearing of the pilots. And jet aircraft so cockpit noise in jet aircraft is mostly due to airflow at hundreds of miles per hour. 3x3 contingency table shows 61 observations of data collected by an airline pilot using a handheld sound meter in a certain aircraft. Noise level is defined as low, under 88 decibels, medium, or high. There are 3 flight phases: climb, cruise, and descent. So climb is B. So the first thing says, what's the probability of B? So B is all climbing flight, or all climbing segments. So there's 30 of those. So all I'd have to do is say how many are there, sum down the column, and then divide that by 61, because there's a total of 61. So. L, same sort of thing, except for now I've got the rows. So sum across that row, and I get 20 divided by 61. And conditional on C, All right, so here we're conditioning on C, the event C, which is cruise. That's this column. What's the probability of H? So it's going to be 2 divided by 11. So there's 2H out of 11 C's. So part C says probability of H given C. There's two ways we can do that. This is either the probability of H intersects C divided by the probability of C. Probability of H intersect C is 2 divided by, so here's the 2, divided by 61. So there's 2 in C and H. So that's 2 over 61. And then I divide that by C, which is, we just found C, probability C is 20 over 61. So this is 2 divided by 20. 61s cancel out. But I could have done that same thing by saying, oh wait, C. I did C wrong. That's not a C, that's an L. Sorry. That should be 11. Or I could alternatively say, how many are there in C? There's 11, and 2 of those are H. So H, 2 divided by 11. And we already looked at, we'll skip the other ones, but and we did talk about the intersection as well already. So L and B, intersection of L and B is 7. So I'm not conditioning on anything, so it's 7 divided by 61. I guess these are all part of number 1. Part of A. Okay, other questions? All right. In just the last 5 minutes or so, I'm gonna just introduce, or not introduce, but discuss the some of the discrete random variables that you should have viewed videos on and read up on already. Discrete random variables are what we call countable, or there's a countable support, or in other words, the values that the random variable can take on are countable. Doesn't necessarily mean that it's finite, could be infinite, but as long as you have a way to, a method for counting, then it can be infinite. So these are going to be things like the binomial, the Poisson, and the hypergeometric. We also, I guess, have talked a little bit about the uniform, which is just like a 6-sided die. The binomial is one that's used to count the number of successes in identical trials. So if you think about shooting free throws, somebody shoots 70% free throws, then you could say, what's the probability? So if X is binomial, they're going to shoot 10 free throws, and there's a 0.7 probability of success. You could say, what's the probability that they make 6 of those free throws? And for any of these random variables, we're going to have a function, a probability density function, written as P of X equals X, that tells us the probability. So for binomial, this P of X equals X is going to be n choose X times pi to the X times 1 minus pi to the n minus X. And so we could plug in these numbers. 10 choose 6 times 0.7 to the 6 times 1 minus 0.7 to the 4. And what that says is we made 6 out of 10 free throws. And what's the probability of making one free throw? It's pi. So any free throw that gets shot, there's a probability pi of success. So this is saying we made 6 of those. So we had 0.7 times 0.7 times 0.7 6 times. But we also missed 4 of the free throws. And the probability of missing a free throw is 1 minus pi, so 0.3. So we have 0.7 to the 6th power times 0.3 to the 4th power. And then we didn't say anything about the order, right? We could have made the first 6 free throws and missed the last 4. We could have missed the first 4, made the last 6, or any sort of combination. And that's where this choose comes in. 10 choose 6 says, how many ways can I rearrange misses and makes, or successes and failures, such that I've got 6 of one and 4 of the other. So I can plug all that in. If I've got a calculator, probably I can find a function on that to do it. But the easiest way to do this is to come over to Excel and say BI. So here's n, here's pi, and here's x, and we'll say probability that x is equal to x. So I'm going to put in 10.7, x is going to be 6, and now p of x, here's the interesting thing, we're going to use a function called binom.dist. Question?
What may be expected to do this in
On the exam, you will have access to Excel. I thought I told you guys. Did I not tell you that? That's the good news. What? I was looking into it. I thought I told you guys last week, but I guess I didn't. Maybe I must have missed that. But Excel will be something you can use on the exam. And it's 2 weeks away, so there's plenty of time to get this stuff figured out. So binom, binom.dist. The first argument is going to be x, and you can see down here it says number s. That's the number of successes. That's 6. Number of trials. That's going to be 10. Probability of success is 0.7. And then the last thing says, do you want this cumulative or not cumulative? In this case, we want not cumulative because we're saying we want the probability x is equal to some number. Cumulative means we're adding up from 0 up to that number. So we put in 0 and we get about 20%. To illustrate the difference, let me put probability x is less than or equal to x. And this is going to give us the cumulative probability. So this is going to be binom.dist. X is 6, n is 10, pi is 0.7, and then we say 1 for cumulative. And so we see there's a 35% chance of seeing 6 or less free throws made out of 10. All right, so this notion of the cumulative probability is really important. You're going to make sure that you understand this. It comes in very handy. It doesn't matter what distribution you're dealing with, Poisson, hypergeometric. I'm going to refer you to the videos on those. But if I say I wanted to know what's the probability that x is greater than or equal to, say, greater than 6. How would I find the probability of being greater than 6? Well, that's just, how are we going to do this? 1 minus the probability that x is less than or equal to 6. So again, the complement rule comes into play, and we'll say probability x is greater than x. That's going to be 1 minus that thing. So why the reason that the cumulative probability is so useful is because I can make things simpler by saying, well, if it's greater than 6, in this case maybe it's not simpler, but instead of having to write out probability that x is less than or equal to 6, that's the probability that x is equal to 0 plus the probability that x is equal to 1, and so forth. That's kind of a pain in the neck. If I have a calculator, or even with a computer, it's kind of a pain to do that 7 times. If I just use the cumulative function, I just call the function once and it does it for me. So, questions you guys have? If there are no questions, then I'll see you guys next week. Again, 2 weeks from today is the midterm exam. I will be talking about it. I did get it sorted out to where you can use Excel on the midterm. And yeah, question.
It's gonna be in like a computer lab.
It will be in a computer lab. Yep, you won't bring your own computer. It'll be in a computer lab, and I'll let you know where that's going to be next week.